Hello, everybody. My name is Surya Venkatesan, and I worked on this project titled Predictive Modeling of Chronic Eye Disorder Risk Across U.S. Demographics with my partner, Shelia Reagan. Our goal was to build interpretable models that support public health decisions by identifying high risk populations using accessible demographic and clinical data. Let's get right into it. Now let's talk about the background and significance of chronic eye disorders. Chronic eye disorders like cataracts and glaucoma and macular degeneration are the leading causes of vision loss across the United States. Over 3.4 million Americans aged 40 plus are affected, and this is expected to double by 2030. Vision impairment is linked to other chronic conditions and costs the US $134 billion annually. Why does early detection matter? Many eye disorders progress silently and are diagnosed late. Predictive modeling helps identify high risk groups early, enabling proactive care. Most research models rely on retinal images and deep learning, which require specialized tools and, to be honest, lack transparency. Public health needs more interpretable models using accessible data like demographics and clinical codes. In this study, we aim to build models to predict eye disorder risk using national data. We use SQL for pre-processing and Weka for modeling. Our goal was to support public health decisions with accurate interpretable tools. Talking about the data next, we used a publicly available dataset titled What You See on Screen, sourced from the CDC Vision and Eye Health Surveillance System. This dataset contains 63,000 plus records and captures a wide range of eye health indicators across the American demographic. Each record includes the information on the year of data collection, state level location, and specific eye disorder category, such as retinal detachment and defects. The data is then structured to reflect crude prevalence rates of treated eye disorders broken down by age group, sex, race, ethnicity, and geographic location. Each entry also includes a confidence interval for the reported prevalence, helping us assess the reliability of each estimate. Next is looking at how the dataset captures demographic and clinical information. Each record includes age, categorized into meaningful groups like 0 through 17, 18 through 39, 40 through 64, and 65 through 84. This allows us to analyze risk patterns across different life stages. Sex is recorded as male, female, or both, and race/ethnicity standardized as all races, reflecting aggregated population level data. From a clinical standpoint, the dataset focuses on all patients and reports total presence for each demographic slice. The key metric is data value, which represents the crude prevalence percentage of treated eye disorders. To ensure statistical reliability, each record also includes low and high confidence limits, giving us a range around the reported prevalence. We also engineered a new variable called risk level, which classifies each record as high or low risk based on whether its prevalence exceeds the median for its disorder category. Finally, each entry is geotagged with latitude and longitude coordinates, allowing us to map trends across the United States. This structure supports our case, building classification models that predict risk level of chronic eye disorders using accessible, interpretable data. So this is the first step of pre-processing on SQL. We start with the data and remove the injuries and burns entries and eye exam entries because these are ocular injuries and routine eye exams, not the chronic diseases we are targeting. Then we drop the undefined sex and age entries. So this is for the records where sex is labeled as both sexes and or age is labeled as all ages. This is because they do not meaningfully contribute to analysis. At the end of this, we are left with over 29,000 records from the original 63,000 plus. Still a good number. We continue pre-processing here by calculating the median prevalence for each eye disorder category using SQL's percentile cont zero point 0.5 function. This allowed us to establish a benchmark for what constitutes typical prevalence within each condition. Next, we joined this median data back into our filter dataset and created a new column called risk level. Each record was classified as either high or low risk depending on whether its prevalence value was greater than or equal to the median for its specific category. This binary classification was essential for training our models to distinguish between higher risk and lower risk demographic groups. It also helped simplify the modeling process while preserving meaningful variation across disorder types. The data we had was all demographic without any unique patient identifiers, so we added row identifiers using the built-in SQL functions to make the split into training and validation possible. We selected 70% of the data for training, and then whatever row ID was not in the training set went into the test set. Given that we had approximately 30,000 entries, a 70-30 split made the most sense here, with around 20,000 for training and around 10,000 for testing. So we ended up with our independent variables being age, sex, state abbreviation, category, and data value, which is the prevalence rates we were talking about, as well as data value unit, which we later excluded through feature selection, but it was supposed to tell us the metric of measurement for the data value because it was not all measured with the same metric. And our dependent variable was risk level, the one we created. For feature selection, we use the supervised method info gain attribute evaluation in Weka. This technique ranks attributes based on how much information gain they provide in relation to the target class, which in our case is risk level. We pair this evaluator with ranker search method to systematically assess the predictive value of each feature. This was done on the entire dataset of 29,000 plus instances, ensuring a comprehensive evaluation. This is the feature selection output. The top ranked features were age with a score of 0.0447, category with 0.0427, state abbreviation with 0.0268, and sex with 0.000205. These four attributes were selected for model training as they contributed the most predictive value. Unfortunately, all the attribute values are low to begin with, so we just kept anything that wasn't an absolute zero and moved on, since we needed independent variables to run classification. This means we excluded data value unit. We didn't include data value to begin with since risk level is based on data value and we didn't want to repeat information. So using our 70% training and 30% test, we ran four classification models: logistic regression, J48, random forest, and naive Bayes. These were evaluated using accuracy, which just tells us the total percent correct, ROC area, which tells us how well the model separates classes, precision, which cares about false positives, and recall, which cares about false negatives, and the cone kappa, which tells us how the model competes with random chance, how much better it is than random chance. So J48 was the best one, and we'll just talk about that in the results section. Let's start with logistic regression, which achieved a ROC area of 0.707 with true positive rates of 0.673 for high risk and 0.611 for low. Precision and recall were around 0.645 and the cone kappa was around 0.285. It correctly classified 3,200 plus high risk cases, 2,500 plus low risk cases, but still misclassified over 3,100 instances. The J48 decision tree performed better. Its ROC area rose to 0.746 and F measures improved to 0.687 for high risk and 0.656 for low. Cone's kappa reached 0.344 and it correctly classified 3,200 plus high risk and 2,700 low risk. Overall, J48 performed better than the logistic regression in both accuracy and interpretability, making it the most suitable model for public health use. Next is the random forest. It was stable but weaker than the J48 with a ROC area of 0.681 and an F measure of 0.646 for high and 0.591 for low. Cone's kappa was 0.237. The confusion matrix revealed over 3,300 misclassifications. Naive Bayes performed slightly better with an ROC area of 0.704 and a kappa of 0.281 and F measures of 0.675 and 606. It still correctly classified more cases than random forest, making it stronger overall. Still, both models fell short of our J48, which is still the best. Now let's compare the models based on three metrics: ROC area, precision, and recall. Feature selection generally improved efficiency and interpretability, making the model simpler without losing too much predictive power. For ROC area, J48 improved from 0.712 to 0.746, showing stronger discrimination. The other three models saw slight drops, meaning they became more interpretable but a bit less accurate. Overall, this comparison shows the trade off between simplicity and performance and confirms the J48 model as the most viable one. This slide compares precision and recall for all four models with and without feature selection. Feature selection clearly helped J48 and random forest. For J48, precision jumped from 0.304 to 0.672 and recall from 0.245 to 0.672, a big improvement. Logistic regression had higher precision without feature selection at 0.698, but its recall dropped sharply to 0.235, meaning it missed many positives. Naive Bayes was the most stable overall, though it also improved slightly with feature selection. Overall, feature selection streamlined the models and improved balance, especially for the J48, and it kept the J48 as the most viable model. In summary, we developed and evaluated four models: logistic regression, J48, random forest, and naive Bayes to predict chronic eye disorder risk using structured demographic and clinical data. The dataset came from National Public Health Records, was preprocessed in SQL, and analyzed in Weka. Feature selection with InfoGain highlighted age, disorder category, sex, and state as the most informative predictors. J48 delivered the strongest results with an ROC area of 0.746 and both precision and recall at 0.672. Feature selection improved interpretability and precision, especially for the tree-based models. These findings show that structured data can effectively classify eye disorder risk, and the J48 model is especially well suited for public health, where transparency and interpretability are key. The gains in precision and recall after feature selection underscore the value of reducing noise and focusing on high value attributes. Naive Bayes also showed consistent performance across conditions, demonstrating robustness with categorical data and potential for scalable public health tools. Overall, our results support integrating machine learning into vision health surveillance to identify high risk populations earlier and enable targeted interventions. Our study had several strengths. We used a large nationally representative dataset of nearly 30,000 records, ensured data quality with rigorous SQL preprocessing, and compared four classification models for a well-rounded evaluation. Feature selection also improved both interpretability and performance, especially for the J48 model. Limitations included missing clinical variables like comorbidity codes, a binary risk classification system that may have oversimplified the clinical reality, and the lack of external validation, which limits generalizability. Future work should explore ensemble methods, add richer clinical features, and validate on external datasets. These steps would improve generalizability and strengthen the role of machine learning in public health surveillance for early risk identification. In conclusion, our study showed how machine learning can classify chronic eye disorder risk across the US demographics using structured public health data. We used SQL for preprocessing and Weka to build four models: logistic regression, J48, random forest, and naive Bayes. The J48 tree proved the most effective, balancing accuracy, interpretability, and practical utility. Feature selection with InfoGain further improved performance by reducing noise and highlighting key predictors like age, disorder type, sex, and geography. These findings highlight the value of predictive analytics for early identification of high risk populations and more targeted interventions in vision health. While limitations remain, such as missing clinical variables and no external validation, this work provides a foundation for future research. Expanding features, validating across populations, and integrating into public health systems could increase real world impact. Overall, this project demonstrates how data driven approaches can support scalable and interpretable solutions to improve vision health nationwide. These are our references. And thank you so much for watching